Hi, welcome to AP Calculus for East Aurora High School. Today we're going to look at the final limit definition of the derivative. This is sometimes called the alternative form of the derivative. You'll notice that it's still based on taking the slope of the secant line and moving one point toward the other point so that we can get the slope of the tangent line. So you'll notice that I identified 2 points on my graphing figure here, so you'll probably want to draw this in your notes. First of all, you'll see this point right here, which is called the point C. So it's got an x-coordinate of C and an output of f of C. Then we're going to look at this point right here. That's got an input of x and an output of f of x. So when I take the slope of the green line that represents the secant line connecting those 2 points, I get this formula right here. Change in y over change in x. So f of x minus f of c over x minus c. Well, if we want to convert this secant line to a tangent line, then we're going to take a limit as the x value approaches the c value. So as the x value approaches the c value, this point right here is going to approach this point right here. So then we will have a tangent line slope. So once again, our designation for that is f prime of c. F prime of c is going to mean the slope of the tangent line at c. So I'm going to mark that right here. So we're going to practice with this formula today, and using in our first example the function f of x is equal to 6x squared minus 3x, we want to find the derivative at the point c equals negative 2. And then we're going to take the next step and find the equation of the tangent line at that point as well. So using this limit definition of the derivative, I can write this as f prime of negative 2 is going to be equal to the limit as x approaches negative 2 of f of x minus f of negative 2 all over x minus negative 2. So this, of course, is going to be equivalent to the limit as x approaches negative 2 of my function, which in this case is going to be 6x squared minus 3x. And then I'm going to subtract the function value that I get when I substitute negative 2 in for x. So that's going to be 6 times negative 2 squared minus 3 times negative 2. And make sure you subtract that whole output. Divided by x minus negative 2, which of course gives me x plus 2. Now let's go ahead and calculate that. So I'm getting 24 plus 6, which is 30. So I'm going to have the limit as x approaches negative 2 of 6x squared minus 3x minus 30 all over x plus 2. Now I see that I can simplify the numerator by dividing everything by 3, so I'm going to factor out that 3, and that will leave me with 2x squared minus x minus 10 all over x plus 2. So once I factored out that GCF of 3, I have 2x squared minus x minus 10, which can be factored into 2x minus 5 times x plus 2. So those x plus 2's are going to cancel for us, and when I substitute negative 2 in for x to get this limit, I'm going to get 3 multiplied by 2 times negative 2 is negative 4, minus 5 is negative 9. So this slope turns out to be negative 27. So that's going to be the slope of the tangent line at the point negative 2. Now I'd like to go ahead and make the equation of the tangent line. Again, remember that our input was going to be negative 2. Our output, when we substituted negative 2 into our function, turned out to be 30. So to make the equation of the tangent line, we are just going to say y minus 30 is equal to negative 27 times x plus 2. Go ahead and simplify that. For my slope-intercept form of that tangent line, I got y is equal to negative 27x minus 24. Now, of course, we could check that answer by entering our original function into our graphing calculator. Then, of course, we would like to enter into our graphing calculator the equation of the tangent line. And when we do that, we should see that those two intersect at c equals negative 2. And the tangent line should look like it's tangent to the curve at that spot. You're going to have to adjust your window to take a look at that. Taking a look at example number 2, we're going to find the derivative of the function f of x is equal to 2 over x plus 3 at a c value of negative 2. Sometimes it's helpful once I have my function and my c value to just go off to the side and say, okay, what's my f of c or f of negative 1 going to be equal to at this point? When I substitute negative 1 in for x, I see that I'm getting a function value of 1. So that tells me that my ordered pair is going to be negative 1 comma 1. Now we want to go ahead and find the slope of the tangent line. So we want to find f prime of negative 1 by saying the limit as x approaches negative 1. So you'll notice that this is different than our previous two formulas for the limit definition of the derivative, because the previous two made the distance between the 2 points that we were talking about go to 0. This has our x value at our x generic point move closer and closer to the c value. So we now want to say f of x minus f of c all over x minus c. So for this example, we're going to say the limit as x approaches negative 1 of my function 2 over x plus 3 minus the function value at negative 1, which we calculated it to be 1, all over x minus negative 1, which gives us an x plus 1. Now, as has been the case in the past, when I substitute negative 1 into this function, I see that I do get the indeterminate form. This one happens to be in the form of a complex fraction, so I want to multiply the numerator and the denominator by the least common denominator, which is x plus 3. So in this case, what we're going to do is cancel off the x plus 3 in the first fraction with the x plus 3 that I am multiplying by. So that ends up giving me a 2 for my first fraction, minus the quantity x plus 3, so that's going to be a minus x and a minus 3, all over, and then I'm going to leave this in factored form, x plus 1 times x plus 3. So when I simplify this, I'm getting the limit as x approaches negative 1 of negative x minus 1 all over x plus 1 times x plus 3. Now let's go ahead and cancel off our numerator and denominator, which are just negatives of each other. So that ends up giving me a negative 1 over x plus 3. Go ahead and substitute negative 1 in for x. So I see that the derivative, or the slope of the tangent line at negative 1, is going to be negative 1 over negative 1 plus 3, which is 2. So I'm getting a slope of my tangent line of negative 1/2. This then allows us to make the equation of the tangent line. So our tangent line equation, we're going to use that slope that we have just calculated, negative 1/2, as well as the point that we calculated at the beginning, negative 1 comma 1. So we'll say that our tangent line equation in in point slope form would be y minus 1 is equal to negative 1/2 times x plus 1. I do like to simplify this, so I'm going to say y is equal to negative 1/2 x minus 1/2 plus 1, so that's going to give me a plus 1/2. So that's the equation of the tangent line. And once again, I can check that by substituting my original function into y1 on my calculator, putting this tangent line equation in y2 and see that they are tangent at -1. For our last example, we'd like to find the derivative of the function f of x equals x squared plus 5x minus 3 at the point c equals 4. So we would like f prime of 4, that's going to be the limit as x approaches 4 of f of x minus f of 4 over x minus 4. Now take a minute and substitute the necessary substitutions into this formula and come back and see if your work matches mine. So I've substituted the function x squared plus 5x minus 3 for f of x, and then I find the function value at 4 to be 33, so I subtracted that. When I combine like terms, I've got x squared plus 5x minus 36 over x minus 4. So factoring the numerator gave me x plus 9 times x minus 4, but it's all still over x minus 4, allowing us to cancel off those x minus 4s. So when I take the limit as x approaches 4, I'm substituting 4 into x plus 9, and that's giving me a slope of 13. So the derivative, f prime of 4, is equal to 13. Now we're going to go ahead and use that for our slope of the tangent line. Let's make the equation of the tangent line. By saying y minus my y-coordinate, so y minus 33, is equal to 13 times x minus 4. Go ahead and simplify that and come back and check with my answer. In simplified form, I have that the equation of the tangent line is y is equal to 13x minus 19. So we've practiced today with some examples showing the alternative form of the definition of the derivative. By the end of this unit, you need to know how to use all three of these limit definitions of the derivative, and we're going to see in class how we're going to recognize these formulas and represent what they mean mathematically. So make sure that you are aware of this formula, put this formula on your gold formula sheet, and we'll be practicing with these in class. Have a great night. Bye-bye.